We have a webinar on electrical design and verification, November 22nd. Warm welcome to all of you. So my name is Dominic. I'm one of the founding member and responsible for conducting events, webinars for NFE. We have almost now, this is 198th, 198th webinar of NFE in just 30 months. Now you can imagine, what effort goes behind conducting the webinars, the time that we spend on front of the camera. I just was giving a lecture in some of the NFE event. Our president, Mr. Gopakumar, has spent 1,800 hours in 30 months in traveling length and breadth of the country to talk about electrical safety. Likewise, everyone here in the NFE, we're spending at least 30 to 40 hours in a week trying to educate people on electrical safety. So, electrical design verification is a subject that Mr. Nandu Gopan is going to talk about it. You know why we are talking about this subject? Electrical design and verification, not just a technical step, it is a line between safe installation and potential failure. So with the National Electrical Code of India 2023 coming into sharper focus, today's session will empower you with practical insight, avoid design errors, ensure compliance, and achieve measurable cost optimization without compromising safety. So Nandu Gopan was also actively involved in BAS and is also guest lecturer at BAS training center. So I would request everyone participating today. We have a tremendous response. We have over 600 plus participants today in today's webinar. So I would urge you to post all your questions only in Q&A box. This will be 45 minutes or maximum 15 minutes presentation, and we will have 30 minutes maximum taking up your question answer. And please be very specific to your question should be very specific to today's topic. Once again, I'm saying your question should be only on the specific subject that we are doing today. And we will pick up a couple of questions. If possible, then we may go live also with individual who will raise your hand. But kindly be attentive. I know Saturday weekend, it's a lovely day to be relaxed. I'm sure next 1 hour, the information that you may share can change the way you think about electrical safety. And I would like to just introduce what is NFE. We are one of the largest growing society in India today, largest society, engineering society in India, with 12 chapter, 3,000 members, and these 3,000 members are active 3,000 members. If not that, they are not renewed. And we are so happy. Every day we get around 40 to 50 new members in NFE. I'm very proud about the achievement that we have done in very short period. And the mission to make every electrical installation free from accident. Our mission is to strive hard through our vision to getting accredited our products and personal certification, which will focus on electrical safety by design, manufacturing, installation, and maintenance of electrical. So what we do, create awareness on electrical safety, improve the skills of practical electrical engineers, practicing electrical engineers, improve the safety measures followed in the industry. I would urge those who are not members of NFE, it's very simple. Just go to our website, nfees.org. Within a minute, you can become a member. Very soon, we will be launching a scheme for 3 years, 5 years, and 10 years for individual who wants to take up a longer duration membership. And I would like to just play a corporate video of 2 minutes of NFE. Let me see whether sometime I get stuck on the technical glitches. I'd like to share the corporate video of NFE. Yes.
Electricity is the heartbeat of modern India. It lights our homes, powers our industries, runs our hospitals, and connects every corner of our nation. Yet behind every switch and circuit lies a silent responsibility, the responsibility of safety. Every year, thousands of electrical fires and accidents remind us that one loose connection can change lives forever. According to national data, over 25,000 electrical fires occur annually, claiming lives, destroying property, and halting progress. Most of them could have been prevented through better design, better supervision, and better awareness. The country witnessed repeated accidents and increase in casualties due to poor installations, lack of inspection, and absence of accountability. They decided to take action. Thus began a movement, the National Federation of Engineers for Electrical Safety, NFE. Started with a small group of like-minded professionals with only passion and purpose. They began spreading awareness through webinars, workshops, and training sessions, one city at a time. What started as a conversation soon became a nationwide movement for safety and change. In just a few years, NFE has grown into one of India's fastest-growing engineering societies, uniting over 2,500 plus engineers across 12 chapters in India. Each chapter drives its mission through learning, collaboration, and public awareness campaigns. NFE has conducted over 180 webinars and 50 workshops on the National Electrical Code of India, in collaboration with the Bureau of Indian Standards, BIS. These programs are helping thousands of engineers stay updated with safety codes, best practices, and new technologies. NFE's signature annual event, ElecSafe, brings together government leaders, consultants, manufacturers, and innovators. It celebrates best practices and showcases electrical safety products that make buildings and industries safer across India. NFE's student chapters inspire young engineers to design responsibly, while its professional programs help experts achieve certifications that matter. Together, we are building a new generation of engineers who think safety first. From a humble start to a national movement, NFE continues to lead with integrity, commitment, and purpose. Because electrical safety is not just a regulation, it's a responsibility. Together, let's build an electrically safe nation. National Federation of Engineers for Electrical Safety. Join NFE as a crusader for change, spreading awareness, training professionals, and advocating compliance.
So I would like to introduce today's speaker, Mr. Nandu Gopan, who is the director of TNG Electrotech Private Limited. He has a strong background on electrical design and safety. Before leading TNG Electrotech, he worked with Cape Electric as an application specialist focusing on EMI and EMC design and electrical design verifications. He has presented papers at prestigious platforms such as International Conference on Lightning, Electromagnetic, and Semiconducting Material, and the 17th International Fire Conference. His article titled Casualty Due to Fire in Air Conditioner, a study on which electrical parameters has also been published. Nandu is an active member in the international IEC, contributing to TC64 and TC81, and is also a member of Bureau of Indian Standard under ETD 20, which is Electrical Installations Selection Committee. As you are aware, this is our 199th. Again, we have end of slide. Sorry, I need to unshare this. Let me see. I'm unshared. Yeah. So, welcome to Nandu, and I'm sure you're going to share your knowledge. And I would request everyone to please put your question only in the Q&A box, and after the presentation, we'll take your questions. Over to you. Over to you, Nandu.
Yeah. Okay, sir. Thank you. Thank you very much for the introduction. So I'll start with the presentation now. Okay. So the topic for today's webinar is on electrical design verification and cost optimization for electrical design. So that is the topic. Now, on to the contents of the today's webinar. First, I'll be showing you some actual site conditions. After project completion, what is the site conditions? Like suppose we have gone for some testings, and what are the readings we are getting over there, and what are the the whether the fault loop impedance and whether it is compliance to the standards. I'll just show some 5 to 3 slides about it to know about the actual site scenarios. Then after that, I'll be taking you on a basic design philosophy for the electrical design. It is pretty much basic thing. It is already mentioned in the standards, but I just want to more emphasize on it. Now, after that, I'll be taking about the fault loop impedance calculation, because in most of the site conditions, the fault loop impedance is not maintained properly. So one of the major ways to do fault loop impedance is you have to calculate it. So I'll be showing you how to calculate it and how to take a disconnecting time, and also I'll be showing you with an example also. So that's not to worry. Then after that, I'll be showing you how to reduce costing in projects. That is just a very basic slide. So I'll be opening some software and I'll be showing you how the projects are designed and what are the things to keep in mind so that you can do a better cost optimization. So now on to the contents. So I'll be showing you some,
Nandu,
yes, sir.
Nandu, once again, there are a lot of comments saying screen is not seen, but I'm able to see the screen. Phone number with
Uh,
Nandu is not correct. 9 digit only. தப்பா இருக்கு phone number எல்லாம் கொடுக்கறது தப்பா இருக்கு சொல்றாரு. Screen is not displaying. Can you unshare and share again?
One second, I'll share. I am stopping the sharing. Now I'll share it again. Screen two.
Some people
Is
say
it?
screen is visible. Some saying, yeah.
Is it?
Can you just
Is
give
it?
your comment if you're able to? I'm requesting the audience. Can you type in the chat box if you can see the screen, the PPT? Yes, go ahead. Now it says visible. Go ahead, Nandu.
Okay. Okay. Thank you. So, I'll just show you some present scenario in the sites. I'll not be showing you what sites it is. So obviously that is for confidential reasons, but just a general scenario on what is happening in these sites. So this is a test which is done on, I don't know, some in some hospital or some in the hotels. So if you see the test reports, the major thing, if you come into the last point, the where I have put the the black box, the black square highlighted part, most of the areas fault of impedance is not actually done. It is above the prescribed limits. Here the limit is something around 0. The allowed limit is 0.423, but the actual loop impedance will be much more higher. Now, due to these reasons, this is one of the reason where fault loop impedance is not coming properly. Now, there are other things also. For example, I'll just take you as in the previous, I've shown a whole report. Now, I'll just show you one report and how do you rectify this error. So first we have to see the protective devices. So they have given some L&T make MCB of some rating 63 amps C type. And the obviously the fault current is going to be for C type. It is going to be 10 times. So it is 630 amps. So the actual fault loop impedance in the site scenario is the disconnecting time is 0.2, and the actual short circuit and fault current is going to be 0.5 and 0.5 Ka. 0.5 500 kiloamps is going to come. Now, if you take this scenario as an example, this fault scenario as an example, and the earthing system is TNS, let's keep it that it is TNS. For an MCB of 63 amps, here they have used an MCB of 63 amps C type to trip within 0.1 seconds, you need something around 630 amps of current. But here we are getting only 500 amps or 550 amps of current, so we need 630 amps of current. So how do you rectify it? Yeah. The only simple rectification in this test report is if you change this type of MCB, the model, the curve from C type, if you change it to B type, that is more than enough. For example, if you take it as a B type is 5 times. So if you take 5 into 630, it's something around 315 amps. So if you put a B type MCB, it is going to, whenever the fault is going to exceed 315 amps, it is going to trip. And in this case, since the fault is 500, it is going to trip. So these are the very, very simple rectification which can be done in the industry. And most of the, fault which is coming in the industry is from the after the main circuit breakers in the sub DBs where the wiring is not proper. In those areas only these faults are coming, and you don't need to make a very big change like you have to reroute the cable or all those things. Sometimes, or in most of these scenarios, a simple change is well enough to have a better protection. Now onto the site scenario. Yeah, now I'm just showing you about the load current and the MCB ratings also in the site. Like for example, sometimes, okay, you can't say it for sure, but sometimes you will not be able to give the correct load details, or sometimes the consultant or the designer will also not put the correct diversity factor. But most of the designs, if will be over designed. For example, here at the site, we have gone and done a full load test after they have confirmed that they have on the all the equipments. The full load current is something around what 12.1 amps, and the MCB rating we will be putting something around 63 amps. So we are telling them to reduce the rating. So most of the actual site scenario is based on this. Yes, there are you can't say this is the fault of the designer, or you can say this is the fault of the installer. There are multiple parties allowed. Sometimes the client can say that I need to in future I'll be increasing the load, so I want you to put in this size. So based on that, there can be some discussions which can happen, but most of the site scenario is based on this. The fault current will be something, the full load current will be 8 amps, MCB will be 40 amps, always over designed. Now, this is one test report. The other one is an example of this where you can see here clearly that the number of the conductor is something around 300 300 CSA 3.5 core, and they have run 4 runs of it. And then they have run 4 runs of it, and then there is this MCB of L&T make. But when you come to the actual load current, here the fault loop impedance is all matching. But if you come to the actual load current, again it is very high. Again, the in the protective earth 600 milliamps of current is going. I don't know if that is very dangerous. That is very much dangerous. But the current is also very, 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 very much less. So if you summarize it, it will be in all scenarios, it will be like this. So the load details, the load which is given by the client, or generally the load which is, if you are getting it from some manufacturer, they'll be giving a much more higher load. So generally the load details will be over designed. Because of that, the cables will be over designed, and because of that, the protective devices are over designed. And here, since we emphasize on voltage drop more, and we are also there will be some cable manufacturers who give a thumb rule for few current carrying capacity of cables. They'll be giving some thumb rules, and they sometimes they differ region to region. Because of these things, most of the times the cables are over designed, and the protective devices because of it is also over designed. And also one more point is the improper fault correction. So the overall cost of the project is increased, and the rather than the cost, this is much more important, the safety is compromised. So that is the much more important point than the cost here. Now I will just show you a basic design philosophy. This expression is there in IS 732 clause, I think 4.4.41. So it is there in this clause for clause 4.4.4.1, which is talking about overload protection. There is one more expression below this which talks about how the protective device need to be sized for the overload current for MCBs. So you can also go to this clause and you can see the expression down below which explains about that. But I'm not going to take on overload and all those things because that is not today's webinar about. So when you come and see this expression, IB means design current for that circuit, and IN means the rated fault current of the protective device, and IZ means continuous current carrying capacity of the cable. This is after derating. So when you take these factors into consideration, rather than putting a load and then checking the cable size and then checking the protective device size, what we are supposed to do is first supposed to select the we are first supposed to make sure the design current is correct. After that, you are supposed to select the rating of the protective device. After selecting the rating of the protective device, you are supposed to select the current carrying capacity of the cable, and then you have to see the voltage drop and all those other things. So this is the scenario. So load details. From that, you decide the protective devices, the rating of the protective device from the load, and after that, you check the cable sizes. Now, I'll just give you an example. So suppose the load is 6 amps. The MCB rating, if you're going to put an MCB rating can be 6 amps or above. Okay, you can ask why are they putting 6 amps? Won't it trip? Or there is this conventional tripping time and non-conventional tripping time. Those times are there. 1.33 and 1.45 is there. So only after 1.33 will the MCB will start to trip, and after 1.45 of the rated current, if 6 into 1.45, that is where the MCB will trip in 1 hour. So that expression is there. So you can go with 6 amps or above. Generally, it is better to go with above. Suppose you can go with something around 10 amps, you can go MCB. And the cable rating should be 8 amps. So suppose here you're going with a 10 amps MCB, then the cable size should be for the 10 amps MCB. So I'll just write it one second. So if you're going with a 10 amps MCB, like due to some client or anything like that, if you're going with 10 amps MCB, then the cable should be rated for 10 amps or above or above. So this is the basic expression here, which is very much important. So after that, you are supposed to look into the voltage drop and all those other things. But this is the basic expression, so that if you will not be oversizing the protective devices, you will be correctly sizing it, and you will also have a approximate good size of cable. But obviously sometimes there are some practical concerns in the sites also. We can't ignore it, because sometimes clients can come and say that I want to increase the load after a certain point. It's a valid point, but even if you want to increase the load after a certain time, it is better to plan in such a way that the load current, the protective device size is always designed to the load current at that scenario. So if they don't have any budget or all those concerns, that is a secondary thing. But for on the point of topic, it is always better to rate the protective device to the cable. If you want, you can increase the cable size and put. But obviously, you can't put a very higher rating cable to a small protective device. You won't be able to fit it in the terminal. But that concern is also there. So now on to the topic. So this is the basic design philosophy on how I explained it. If you do this, it will be good. And it is the standards are actually suggesting that you are supposed to do it in this method only. And I'm not talking about like overload here. And now let's go to the next topic, which is calculation of fault loop impedance. So I hope nobody has much questions on it. So even if you have questions, put it in the Q&A box. Probably I can address to it later. Now, calculation of fault loop impedance. How do you calculate for a model circuit? Because most of the site scenarios, it will not be as per the fault loop impedance. Like fault loop impedance is the minimum criteria over there, so it is to be looked after. So you have a source. I'll just explain this thing. So you have a source, maybe a transformer or a DG, whatever, or you have it is coming from a public distribution that also can be added as a source. So here I'm going to take this source as a transformer. So you have a source. From the source, it is going to a main panel. From the main panel, it is going to some sub dB. Then it is going to a final dB, and then it is going to a socket. So let us take in this place. So in this place, it is 230 volt. So to calculate the impedance, the fault loop impedance of the source, first you have to calculate the impedance of the source. I'll be showing you how to calculate it. Then after that, you have to calculate the impedance of the line conductor. Suppose if this is the line conductor, and you have to calculate the impedance of this impedance you are supposed to calculate. Like that, you are supposed to calculate for whole line conductors, and you are supposed to calculate the impedance of the whole P conductor. So that's what I've written here. Impedance of the line conductor, 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 and you have to add it all with the impedance of the earth conductor. So this is the basic philosophy. If you add all these values, you will be getting a value of ZE, that which is in terms of ohm. Now I'll take a model, ratings and all those things. So from that I can explain how do you make those calculations. So impedance of the source. Impedance of the source, I'm taking this as a model rating, which is rating of 315 amps, 350 kVA, 315 kVA per rated power. And the face-to-face voltage is 433 volt, and the Z percentage is 4.75 percentage. So first is you have to add that. With the line conductor, I'm putting a line conductor of 240 square mm, length is 25 meters. P conductor is also an aluminum conductor. I've considered an aluminum conductor. So in sub dB, this is the square mm 95 and T. And in ZP, in the P conductor of the sub dB is 50 square mm 50 meters. And this is 16 square mm copper into 50 mm 50 meters. Here also I'm putting the same size of P conductor, 16 square mm copper, 50 meters. And then to the socket is 4 square mm copper, 50 meters, plus 4 square mm copper, 50 meters. So when you add all these sources, Z1, Z source, Z1, ZP1, ZL2, 1, ZLP, P2, these things, this thing, this thing, this thing. When you add all these into this expression, you will be making this ZE value. So this is how to make it. Now, so how do you calculate? Okay, before calculating it, I want to emphasize on one point here, which is above that I am here. It is very much in the yellow highlight that reactance is not considered. So I'm not considering reactance in this because if I consider reactance, it is going to be much more complicated, which I'll be showing you much more later why it is complicated. Um, Now I'm ignoring reactance in this loop, and I'm going to talk to you about it. Now the source, as I mentioned previously, it is going to be 315 kVA. Voltage is this same rating, the same specification, and the line is this is the line. And now you have this formula. Obviously, everybody will know in the design industry, you'll have what is the Z impedance by value of it. So this is the value. This is the formula for it. The short circuit, the Z percentage divided by 100 into the voltage square by rated power. So this is the basic formula. It is also mentioned in IEC 60909 part 0. for calculating the ZT. Now the ZT is going to be something around, if you substitute all those values and multiply and substitute all those values, you are going to get a ZT of 0.0283 ohm. So you're going to get, so you already got the ZT of this value. Now, after that, you have to calculate the resistance of the cable, the resistance or impedance of the cable. So for that, it is resistivity by CSA of the conductor, resistivity by CSA of the conductor into length into 100. So I have put all the units here. So if you have any questions on the units, please do look it up here. I'll just remove that also. A second. Yes. So I've put all the units here also. So if you have any questions on the units, just look into it. Second. Okay. So then after this, if you and the resistivity of conductors at 20 centimeter 20 degrees, they have given it in the IS 8130 standard. So in IS 8130 for standard, the copper at 20 degrees is going to be 18.51, aluminum is going to be 29.41, aluminum alloy is 32, and steel is the GI. Steel, what they talk about is the GI which we can use. So if you are, rather than in here, if P conductor you are using GI, then you can use this resistivity value. So, and obviously I'm considering here at 20 degrees. I don't want to complicate the process much, because Krish has done a webinar on the temperature and he has also done on the other factors. So I'm not going to talk about the correction factors. So I'm going to talk only on a general scenario. Now the resistivity, now you have these values. When you obviously substitute the values for ZL1, so it is obviously aluminum is 29 divided by 240 into 25 meters by 100, which is, you'll be getting this value. And ZTE, you'll be getting, if you substitute the same thing, you'll be getting this value. So after getting these values, when you put it in the equation, so in from the previous, we got the Z source, which is 0.0283. ZL1 is 0.0031 ohm. ZP is 0.0061. And ZL2 is, I've substituted those values. If you want to know how I did it, you can watch the YouTube and you can go back and substitute the values. It obviously the same values are only going to come. So 0.0155, ZP, ZL2, ZP3, and ZL4, and ZP4. So these are the values for that. So obviously, when you add all these things, you will be getting Z's, the impedance of the source. So I have added all those things and I'm getting a value of 0.6608 ohm. So this is the impedance, calculated impedance at this point, at the socket outlet. So at this point, you're going to get a ohms of 0.0006. So if you take a loop impedance meter from Sonal or Fluke, and if you go to this socket, and if you plug in that meter, and you put the fault loop impedance calculation, you are supposed to get a value of 0.6608, but you might not get that value, because if you add resistance to it, maybe there can be a variation of 5 percentage. I mean, not reactance. If you add a reactance into this formula, you will get a variation of something around 5 to 2 percentage. You will get a variation. So in this area, you should get close to this value. Now, after doing the calculation, you have got the ZD, which is you already got the Z impedance. Now from that, you have to calculate the current. Obviously, the Ohm's law is there. I is equal to voltage by resistance. So your impedance, and you just do the calculation. And at 230 volt, you will be getting a current of 348 amps. I'm not considering the 2 by 3 factor also. So you'll be getting a current of 248, I mean 348 amps. Now, after getting this value, okay, you have got this value, you have got the fault current at that location, and you have got the what is it? You have got the loop impedance of that location. But with this, you are also supposed to uh, know that your protective device should trip in this fault current. So you have to make sure you are going to select a good protective device. So as per IS 732, the maximum disconnection time is 5 seconds for distribution circuits, and for final circuit it is 0.2 seconds. I'll just explain this. Give me a minute. So in this, if I'm going to take this dB, or if I'm going to take this dB, or if I'm going to take this dB, it is all going to be 5 seconds. Why they have put 5 seconds? That is due to selectivity, so that if this dB can trip, this should not trip, or this should not trip. So they have put a disconnection time of maximum 5 seconds. But for this socket, for this single phase socket, it is going to be 0.2 seconds. So yeah, it is mentioned clearly in IS 732 table 1. And if you go a little bit above this IS 732 table 1, they have given a lot of text on what the distribution circuit is. This is for a TNS system. So if you have a TT system, if you're going to put earth electrode, the disconnection time is going to be much more much more slow, much more the disconnection time is going to be much more less. So now, so suppose you have considered a MCB of, for example, for this calculation, I'm considering an MCB of 32 amp C-type MCB. So I have to make sure this 32 amp C-type MCB is tripping in this fault current. This is what I have to check. Now, the C-type 32 amp C-type MCB will have a tripping characteristics like this. So ABB or Schneider, whatever it is going to be like this only, because it is already defined. So the tripping curve is going to be within 5 to 10 times. So type C is going to be 5 to 10 times. So 5 into IN, which is 5 into 32 amps, is going to be 160 amps, which is going to be this green color line. This is 160 amps. Next, you have 10 into 10 times. You have to 10 into IN. So, which is going to be 320 amps, which is going to be this line. So, while doing the fault to impedance calculation, you are supposed to take the highest amount. You have to take 230 amps. You are not supposed to take 160 amps, because you are not sure whether the actual fault is going to come at 160 amps. If it is going to come less than that, then it is not going to trip. So if you take the higher value, then even if there is a variation of 5 to 10 percentage, or if there is a variation of 20 percentage or 30 percentage also, this protected device will trip. So you are supposed to take the higher percentage. So you are taking 320 amps as the tripping characteristic. So in this, if you look into this characteristics, within 0.1 seconds, it is going to trip in 230 amps or in 160 amps. But if it is going to exceed a little bit, if it is going to exceed probably something around 100 amps here, this region, then it is going to take close to 6 to 7 percentage, 6 to 7 seconds to trip. This is what it means. So you are supposed to limit it to 160 to 320 amps. So we are going to take the 320 amps here as the calculation. Now, okay, I'm not taking these values out somewhere. This is all mentioned in the instantaneous. This is referred in NEC also. In NEC, you can go to this clause or table 14A, where they have mentioned about this tripping characteristics of MCBs. Now, so for an 32 amps C-type MCB to trip within 0.1 seconds, you need 230 amps. Second, I think I made a mistake. Yeah. Okay, I think I made a small mistake, but okay. Leave it. Okay, so this MCB will trip. I've made a mistake here. I just realized it right now. So this MCB will trip. If suppose this fault current is going to be less than 320 amps, if the fault MCB, the fault current is going to be less than 320 amps, if it is 319 amps, then you are supposed to change the MCB from type to type B, or you are supposed to decrease the size of the MCB to 25 amps. So you can do both of these changes. You can either decrease the tripping curve from type C to type B, or you can change the rating of the MCB from 32 amps to 25 amps. So these two things can be done. But let's come to the practical scenario on how, when you are doing this calculation, how many difficulties you'll be facing. So obviously, the example I have showed you right now is for 1 second. The example I've showed you right now is for the one circuit. You are supposed to do this calculation for n number of circuits. You are supposed to do, if you have 100 circuits, you are supposed to do it for 100 circuits. If you have more than that, you have to do it for all the circuits and all the load, final load also. Because you don't know, because nobody can be sure where a fault can start. Now, there are also other things like the correction factors can differ, because I've not talked about correction factors here. If you have different correction factors, then it is going to differ a lot. But the other major issue is going to be the protective devices, different protective devices. So for example, here I have talked about the what is it? I've talked about MCB. For MCB, you will be, everybody knows that the tripping curve is going to be 5 to 10 for C, or for D or B. It is already defined in the standards. But what if you're going to take an MCCB, for example? So if you're going to take MCCB, so give me a minute. I'll just show you how we are going to do it for an MCCB. So if you're going to take an MCCB, so I'll just click this. 1 second, stop sharing. I'll share the screen again. Screen 2. Okay, share. Can anybody see the screen which is there here now? Screen share. Okay, I think you can see the screen. I'm getting some comments that you can see the screen. Okay. So for MCBs, for Siemens, Schneider, blah, 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 all those people, it is very much clear that these are the things you need to do. The MCBs 5 to 10 or C or D type, you can already do it. Now, sorry, 1 second. Just got 1 second. Yeah. So, but what about MCCBs? So when you take MCCBs, for example, I'm taking a specific brand. I'm going to take an ABB MCCB, and I've gone to the MCCB. I'm going to select T-Max XT MCBs. So I go to the page, go to the publications. I come down below. I go to the technical specification here. I click it. Then I check what type of curve I want to go. Suppose I want to go with something around 400 amps. This same type. Just go a little bit down. You have 300 to 400 amps. Time current curve. So I just click. So it is going to open to something. So in this, they have given this tripping characteristics. They have given the tripping curve. Now the problem is I have to check what is the setting of the MCB I want to keep. Suppose you're not going to keep it all these settings, you will sometimes need to change the settings. So now I am going to take maximum. I hope everybody can see my cursor. I'm going to keep it at the maximum. Now at the maximum, this x-axis, the 0.5, 1, 10, 100, 1K and 10K is going to be the multiples of current. This is the multiples of current. And this area is going to be the time in seconds. Okay. So this is 0.01 seconds, 0.1 second, 1 second, 10 seconds, 100 seconds, 1000 seconds. This is the multiple in times in seconds, and this is the multiples of current. So suppose if this is 1, if I'm taking a rating of 300, if I'm taking a rating of suppose 400 amps, this is 1 into 400, which is 400. So for this, it is going to come and trip at this area. It is going to be coming and tripping at something around 600, 200 amps, 200 seconds, it is going to trip. So I have to check it. Now, if I want to trip in 0.1 second, this will be the value. So if I come down below, it is going to be, I have to keep approximately something around 10 to 20 times of the tripping curve. I have to keep, not 20 times, 20, 30. I'm supposed to keep something around 40 or something times of the tripping curve. I'm supposed to get that much fault current. Then only it is going to trip. So 400 into 30 or 40, and I'm going to get how much ever the value, that is going to be my IA. So when you take this design for a huge project, it is going to be very, very much tedious. Yeah. Uh, yeah. It is going to be very much tedious. Sure. Yeah. It is going to be very much tedious. I hope everybody can see it. Okay. Now, okay. So it is going to be very much tedious. If you're going to see for MCCBs of different makes, it is going to be very, very tedious. And for relays, it will be very much other tedious. Now, there is another problem where you have different disconnection times. So suppose you have to get it for 0.5 seconds or 0.4 seconds or 0.2 seconds, it is going to differ. For hospitals, if you don't care about the disconnection type and you are going to keep it everything at the minimum 0.1 seconds, that is fine. But do remember that if there is going to be fault at some X circuit, it is going to affect even your main panel. So that selectivity, or I would say discrimination, will not be there if you are going to keep everything at the same disconnection times. Next problem you'll have while doing this calculation is if you have paralleling of sources. If you have, or you're going to use a different source. So suppose if you are using a DG, you will have a different lower values. Mostly it will be lower value. And if you're synchronizing multiple transformers, it is going to, again have some issues. It is going to have a much lesser loop impedance. And calculations need to be done at all sources. So if you have transformer 1, 2, 3, and DG, you have to do it for all the transformer and the DG. And the other main problem is if you have parallel fault current. So if you're using armoring as a fault PE conductor, if you're using a GA strip as a PE conductor, then it is going to be there is going to be two parallel paths. So that is also a problem. That is going to increase the current and decrease the resistance if you have a parallel path. And another problem you're going to have is going to be the reactance. Okay, for the previous value of previous loop impedance, I have the reactance I have not considered, because if I consider reactance also, it is going to be at max something around 10, 20 to 10% it can increase maximum. But if you're going to have transformers above 1500 kVA, reactance plays a huge part. And if you're going to have cross-section conductors with cross-section above 25 square reactance also plays a huge part in the total ohms of the total impedance of the circuit. So you should not ignore reactance. So if you don't ignore if you ignore reactance and do a calculation, then in a circuit after a certain point in the main panel or in the sub main panel, if you check the fault of impedance, it will be much more higher compared to the designed value. That is due to this reason, because reactance is not considered. Okay, so before that, so due to these reasons, there are some softwares available in the market which can help you in all those things. So I'll just show you about a software which TG Electro is partnering up with another, another company, and which can also have a, which can make the life much more simpler. One second, thought made a mistake. Okay. Okay. I think I made a mistake. I was supposed to. Okay. So this is a software. So I hope everybody can see the screen. Can you all see my screen once again? Yeah, screen to share. I hope everybody can see the screen. So this is a residential complex of we are going to I'm only having the common load of a residential complex now, and they have something around close to three transformers parallel to each other. Not parallel. This is not parallel because the bus coupler is not on. Uh, Bus coupler is not on. You have something around close to three transformers, and it is all going to each load, and this is all going to be the common load. Now, when you take this uh, circuit as an example, at this area, the loop impedance is going to be something around the loop impedance. It will also be showing you all the loop impedance. What is the maximum Z percentage? It will automatically calculate the resistance and reactance. I have put a busbar trunking system. It will automatically show these issues. What I would suggest people is either ask for things like this, or make a proper calculation. So one of the major issues you'll be avoiding while doing these using these softwares, I'll show you a software in a little while, but before that I'll just take a little bit on the PPT. So when you calculate all these things wrong, when you are going to overcomplicate all these fault loop impedance calculations, uh, these are the issues mostly you'll be facing. It is going to affect the costing of the project, obviously. So most of the cables and protective devices are going to be complicated. You are going to have wrong service and ultimate braking capacity of the protective devices. You are going to rely too much on the voltage drop. You are going to have improper calculation of fault and short circuit current in each dBs. And you are going to have, if you are going to have improper load details and many more. So for this, I'll just show you this example. Okay. So this is the residential tower. I'm not going to show about the tower or what client or all those things are. I have removed all those details. So here, if you come to the main panel section, if you just double click it, they'll be showing a fault current of something around 42 amps, or for earth fault current of 32 kiloamps. But major thing is this earth fault current at this location can be 32 kiloamps. But when you come just below it, suppose this downstream, when I'm going to take this streamer, for example, which is going to be this one. Yeah. If I'm going to take this utility panel, the fault current at this location is going to be only 2.755 kiloamps. Obviously, there are some errors in it. There are something around 500 or 600 errors in this. Do ignore this because this is a project which we have got and we are doing some design verification. So when you are going to see the fault current, earth fault current, it is going to be very, very much lower. The earth fault current at this location is going to be 2.77 kiloamps. But at the main panel, it is something close to 32 kiloamps. Now, at the same area, I have to show a little bit on this main panel. If you are doing a proper design, you will also be reducing the protective devices size and also be cable sizes, or you will be increasing it as per the need. Now, here, when you see I've showed you a first example of the design philosophy where you are supposed to keep the design current. Then you are supposed to design the busbar trunking system and all those things. You are supposed to, no, first you are supposed to do the design IB, design load current. Then you are supposed to choose the protective device size. Then you are supposed to choose the cable size. So suppose you take this for example, the IB design current is going to be 0.5, I mean 5050 amps. For this, the cable we have used is something around 32 3 3.2 k amps BTS system we have used. And the protected devices also is rated for 30 to 100 amps. So first thing, when you come to the protected device sizes, you can very much decrease it all the way to 600 or 1600 amps. Or in the same scenario, you can also tell your installer, or you can tell the client, okay, for now I'm going to design it for 1000 to 3200 amps. But you know what? While doing the actual load, you reduce the load to this zero point 0.5 of this specific circuit breaker. So obviously we have all the circuit breakers, ABB, Siemens, Schneider, and all those major peoples are there. So you say you select that specific brand of that and specific model, and you say you're gonna keep at this model, and you click select. Suddenly, you can also reduce your cable size. You can also reduce the BTS size to something around 1600 amps, and you can click apply. So you can, these are the small things which can optimize any design. But obviously you have to note one more thing: the voltage drop at 1600 amps is going to be 0.37 percentage. But if you are going to put at 3200 amps, it is going to be 0.91 percentage. So voltage drop is increasing by 2 times. So that also you need to keep in mind. But also you can reduce the cable size. Now, when you are going to consider all these things, once again, yeah, when you are going to consider all these things and do the good design, you will be able to minimize all these errors in this circuits, and also you will be able to optimize the design to the correct level, what is actually approved by the client, and also what is required by the inspectorates, and what is required by you as a designer or contractor or whatever. So that is what I wanted to show. And there is one more thing you can get from this, is you can get a report. Finally, in the end of the day, you can get a report, something like this, which says that this specific circuit, you will be suppose if you have something around close to 100 feeders and something around close to 1000 load, you will be getting a design report of something around close to 100 or 300, 500 pages report you will be getting. So in this, you'll be getting for each feeder, you'll be getting these values. So what is the what is the conductor size, cross section area? What is it, XLPE and all those things? Second. What is the conductor XLPE or 70 square copper, and whether you are running the conductor at 70 degrees or whether you can run it at 90 degrees, you will be getting this value. You will be getting the actual load, actual current at that value also. Suppose here the current at this value is actually 555 degrees. So maybe in future, if you feel that the temperature is increased, then you can check the connections, loose connections, or if the it is going to be some overload or all these things, you can get the actual temperature rise. You can get what correction factors you have used, what is the ambient temperature of the surroundings used, and you will be getting all these other values, which is going to be the z percentage, what is the percentage of the impedance of the source, and all those things, design current, device tripping current, I mean device, what device you are going to keep, what device setting you are going to keep, what is the minimum effective conductor capacity, what is the current carrying capacity of the thing, and all those things you will be getting with respect. And also you'll be getting some load factors, what is the harmonics expected, percentage harmonics expected, design load, what is the voltage drop at that location correctly, and also the earth fault current and the phase fault short circuit current. You'll be getting all those exact calculations with considering all the correction factors, current, considering the reactance, considering multiple sources, considering multiple runs or multiple parallel paths like armor and GA strips. So this is what is required. So now for the same project, not for this project, for another project, we have just done a small design verification. not design verification. They wanted to do a little bit on the costing part. So I've just made that same costing into a PPT, and I just wanted to show you all on how you will be able to save the amount by selecting the. I'm talking only on protective devices. I'm not going to go into the cables, because if I take cables here, then there can be a problem of voltage drop, and there can be a problem of other correction factors and all those things. So I'm not touching the cables at all. I did for the project, I have reduced the cable size also, but here I'm going to show only on the protective device part. So that is what is much more important. If you that will also save a lot of um, uh, it will increase the safety also. So I'm going to talk only on the protective devices. So you have a 16 amps MCB. They have something around, and I have changed it to a 6 amps MCB, close to 166 numbers. So the cost wise, it is going to be the same cost. Maybe if you have a better costing, I don't know, but this is the costing I have received from people. So please, if you have some better cost, maybe it can be different or all those things. Please ignore it. So 16 amps, 6 amps, so something around 1600, 166 amps. Numbers, it is same. Now they have also used 100 amps MCBs. So we have changed it to 40 amps MCBs, which is close to 15 numbers. The decrease in cost is approximately 80 percentage. You are getting a decrease in that percentage of cost from 100 amps to 40 amps MCBs. When you take 40 amps MCBs, we have decreased it to a 16 amps MCB for that project, which is close to something around 30 numbers, which is a 20% decrement. And other MCCBs, we have overall, we have taken all the MCCBs, which is close to a large number, 40 numbers. And when you, and we have put the correct MCCB ratings with the fault current, the ultimate braking capacity, and the service braking capacity, we have put to the correct number. So that is close to something around 40, and there is a decrement of something around 20 uh, percentage. For example, when you, the overall costing, I'm not really sure, but it came close to something around 20 lakhs. When we take a 25% decrement from all these above numbers, it is coming close to something around 7 lakhs saved. Yes, this is not a big saving in a project, because we'll be dealing it in something around crores or 20 crores or 30 crores projects. Electrical contractors scopes will be there, but this scope for this project, for your information, I'm only showing it for protective devices alone. If you're going to take cables, and if you're going to take BTS sections, and if you're taking all those other components into consideration, this is going to save at the maximum. It is going to save, even if it is a 5% save from the overall project cost, it is going to come in a very big amount. Yes, there can be other type of clients or any contractors, or say they can say that I want to get more safety and I don't care about putting 5 kiloamps. I don't mind putting an earthing system for 5 kiloamps. I can put it for 10 kiloamps or 20 kiloamps. They can say it. But what I would really suggest is, rather than, you can save the cost in all these protective devices, cables, and all those things. And you can also, in the same project, you can, rather than using a cable tie for cable tray, you can put the cost for cable, what is it, clamps for cable tray. You can go with the cable clamps. You can use a cable clamps for all the cables, or you can go with a better quality double compression cable metal glands. All those things can be improved in a project. So rather than saving the cost, I would say it is better to optimize to another same field. That is much more important. And also one more thing, this project is actually a well-designed project. To me, the previous project which I showed you, which had something around close to 100 failures, 1,000, I mean 600 errors. This project had very less failures, and it was a well-designed project. In a well-designed project, if you can save a small amount of cost on a very huge scale project, you will be saving a very good amount of cost. So, like this, I want to conclude. So, thank you very much. So if anybody wants to know about the the costing of the project, costing, or if you want to know about the software I've showed, just you can just write an email to ng@tgelectro.com. I think the phone number is little bit. I think I made a mistake in the phone number also. So, but you can write an email to me. Thank you very
We
much
can collect it,
for this.
Nandu, now. You can just say escape, just change the number, put a number. I would welcome all the participants to put your questions in the Q&A box relevant to the today's topic. So, Nandu, very well explained. You are saying the software that you developed. I think, if I remember, this is in line with National Electrical Code of India 2023. So, all the parameter that you have made it in the software that meets the requirement as per the National Code of India and 2023, and it will not allow, the design will not allow you to deviate or make any mistakes. That's what I understand from your presentation, that software is a tool for designing a circuit in a building, which otherwise takes 10 days. If you use this software, it's just a 1 day work. Am I right? I'm looking from the convenience side of it.
Sir, actually, to be honest, a project, when they are going to start designing the project, they can make a small schematics in AutoCAD or all those things. That is fine. But when they go for the tendering process and when they finalize the contractor, it is going to take some time for them to finish the whole project. So, at that they have to order the transformer, they have to order the DG. At these times, they can make a proper design and they sit with the client and they make a proper design in the software and all those things, then they will be able to do a much better job. I think that is where we are lagging very much in the industry. So, I would suggest to use this software in that area.
So this software is what, available free for everyone, or are you giving on trial basis to all the consultants and those who are in?
There is a trial basis, something around 14 days trial license is there. If you want, I can also extend the days, but there is a 14-day trial license is there.
So, ladies and gentlemen who's listening to this, so Nandu is ready to offer you this software on trial basis of 14 days. So I've seen this software, which if I'm a consultant where I need to have 10 people to work on this design, with this software, one engineer can do. That's what I understood. And in most of our NFE workshops, we demonstrate this software. It's a wonderful tool for not to miss any circuit points and also avoid a wrong design. So let me pick up a few questions quickly. Nandu, here he says the first question, I will take only relevant. I will not take which is not relevant. So allowable fault loop limits. Anup Kumar is asking, what is the allowable fault loop limits?
Sir, actually, we will not be, Anup sir, we will not be actually saying, we can't say a value of this is the limit or all these things. The standard only says that you are supposed to have it disconnected within 0.2 seconds or 5 seconds or zero point 0.1 seconds. So there is no limits, only disconnection times which is there. From that disconnection time, you have to choose the MCBs, and from the MCB, you are supposed to get the loop limits. So this is not an easy answer, but it depends on the which circuit and all those things are there.
Okay.
Okay.
Next question is Deshmukh. You are saying in first slide for 535 amp fault current, just we change the type of MCB, but tripping second will be vary when it is sensitive load is like some equipment type C only, correct type B only for lighting code. Hope you could understand that.
Yeah, I can understand the question. This
Deshmukh,
is actually a valid.
Dinesh Kumar.
This is
Yeah.
Yeah. This is actually a valid question because I have not checked the load at that MCB. I have not checked the load. What I have given at that time is an example. What I've maybe you can change the current or if but If you want to have safety, either you have to change the type of circuit breaker, or you have to change the MCB rating. But before choosing the MCB rating, you are supposed to also check the load. Suppose if you have motor loads, it is better you go with the D type or C type MCB. But if you have lighting, then you can go with B type. But if you have motor, then it is better you don't go with B type, provided you are going with the same rating of MCBs. So if you're going with a higher rating MCB, then it is not going to trip. But yes, that is it.
Venkatesh is asking, B-type MCB, is it allowed to use in the industrial application?
Sir, that depends on what type of load you're going to connect it with. If you're going to connect it with the lights, then it's fine. But motors, then I would suggest not to. You can go with C or D type.
So, Arinder, how to ensure to protect earth leakage in battery rack of UPS?
Sir, actually, this question, there is some
Not
discussion
related
in
to
the NFE
today's.
also. This is not, yes.
Okay,
There is
let's
some,
skip.
there- yeah, on this question, there is some discussion in the NFE group where Apav sir is also giving a lot of comments on it. So we can skip that question.
I don't know, Apostle is there in this group. I just wanted to have him
It's
on
a
board.
very
Let's see.
complicated answer, sir.
Uh-huh. Complicated answer is Apostle is here. Apostle, yeah, allowed to talk. Sir, I have Apostle, I am promote as a panelist. Yes, Apostle there. Apostle, you
You
want to
can.
comment on that? Though it is not a subject, but anyway, I'll keep that in reserve for when you are there. So, Nitin Gorpade, against the demand of copper cable by equipment supplier, we lay aluminum cable. That is against demand of 10 square mm, we lay 16 square aluminum.
Hmm. Uh, there can be other reasons why the equipment manufacturer says it, because generally the equipments are tested for, they are going to, if you're going with a good quality equipment supplier, they will say that you need to have a Z percentage, ZE, they will give a ZE value, and you are supposed to achieve that ZE value in the equipment terminal. But sometimes in India, we say that rather than saying the ZT value, we say about the, we tell about the, you put aluminum cable or copper cable. I will not be able to comment on this, but going with a higher size, I feel it is okay, but I can't give a specific answer. I have to, on terms of safety, it can maybe it can be higher, or you can ask the supplier to give a rating in aluminum, and you can put the same rating. That's not going to be a difference. Name and price of the software, you can just there are multiple ranges in the software, which is going to be, if you're going to do for small homes, it is a different range. If you're going for a house, it's going to be a different range. If you're going to do for a mall, it depends on number of circuit. If you're going to do for unlimited amount of circuits, like suppose hospitals or shopping malls, it is going to be a different range, which is something around 2 lakhs for a perpetual license. You will be owning the license for 2 lakhs. But if you are going to do for small homes, it is going to be something around 50,000 for the perpetual license. So it varies. And
Okay.
the next question.
Next question, Nandu, how do you calculate ZE in software?
Okay, I think ZE actually, it automatically comes in the software when you put the load, when you're not load, sorry, when you're going to put the transformer details, when you're going to put the load, I mean when you're going to put the cable, then the panel, then you're going to put the load. I mean then it automatically comes in the software. What is the ZE of the in the software? So I'm not going to do any calculation, but it automatically comes. I hope that is the question. But if you are asking me how we have to calculate in the software, then I have to show you the previous slides only.
So, Anonymous, is asking what are the standard that is applicable in that software? Which are the standard that you follow?
Okay, this is a very good question. The software is actually based on IEC 60364 series of standard. IEC 60364 is adopted in British as BK 7671, BS 7671, and in India we have adopted as NEC 2025, NEC 2023, and IS 732. So this software is based on NEC and IS 732, and also this IEC 60364.
Okay, Nikhil, Nikhil, most of the existing system available are TT system. Is there provision in software for TT system also for all shown calculation?
Yes, it is there. But while doing the TT system, you will have to be a little bit careful because you have to put the resistance and what is the earth electrode resistance. You have to put those values because if that value is going to keep on changing, in summertime it is going to be 10 and in rainy time it is going to be 1, then you will not be having a very good safety in that area because yeah, that is there. I think this is already
So,
answered, sir. Yeah.
yeah, Dhyaneshwar, a lot of people are asking. Those who are interested to know more about the software, I would urge you to just put a request on the email, the contact details which is given. So once that is done, we will give it to you. Uh, again, uh, the software name, it is developed by Mr. Nandu and his company. Okay. Uh, Sir, Apav sir, there was a question on UPS earthing. Can since he's online, can you just, Nandu, can you just ask Apav sir what is that really is asking for?
One second, sir. Apav, sir, I hope you are online. Apav, sir?
Yes,
I-
Nandu. That I can
yes, sir.
consider
Actually,
that
there is
is
a question. Yes, sir. There is a
okay.
question here. How to ensure to protect earth leakage in battery rack of UPS? Earth leakage protection for UPS, they are asking, sir. You have any specific comments or we will?
I have to refer.
It's
Because that leakage is purely uh, DC. It's a DC voltage. It's also is under a extra low voltage. You don't have a very high voltage. If there is a high voltage, there will be some system. So for low voltage, safety extra low voltage 24 48 volts. Safety requirement is not required for. If there is an inbuilt device that will check up on percent, I know the answer for the options are really specific voltage specific. That's all.
sir. Actually, I
Thank you,
would
sir.
suggest that
Yeah.
this earth leakage for UPS, it depends on various other things. What type of UPS you are having, whether it is isolation transformer is there or all those things are there.
He
So,
is concerned, just a moment, he is concerned with the DC leakage for the battery pack,
okay, okay,
not the
okay.
UPS. If there is a AC side, it can, for low voltage,
Sir,
extra low voltage itself is a safer.
Mm.
I
And
think look like we'll
only
have a one separate webinar on that subject because a lot of curiosity on UPS earthing.
totally, altogether it's a totally different subject of mitigating
Yeah,
Yes,
yeah,
sir.
disease.
yeah.
DC,
So we'll
DC.
let's not deviate from today's topic. Vinish is asking generally, earthing conductor is selected based on the earth fault current. Here, after selecting the earthing conductor, you are calculating the earth fault current based on the resistance. Then, what basis did you select the earthing conductor?
It is vice versa. You can't say like this. We won't be able to say like this. You are going to select a earthing conductor depending on the resistance. It is going the earth fault current is going to vary. If you are going to select a lower size, then at that area at that probably at that location it is going to vary. So you are supposed to select. If you're going to put a higher size earthing conductor, then it is going to have a much more higher earth fault current, and if you are uh, going to put a lesser earthing conductor, it is going to have a yeah. I don't really understand that question much.
You say, okay, anyway, that I'll park that. Vishnu is asking during design stage, how can the cable length be finalized? It depends on the actual site condition.
Mm-hmm. In during the design stage, I would really suggest to go with the higher sized, higher cable length, whatever is there. You can go with that higher length. You will not be able to know the exact cable length. But the problem is, if you don't know about the exact cable length, you will not be able to get the correct loop impedance. And with the loop impedance, you will not be getting the correct voltage drop, and you will not be getting the correct disconnecting time, and it will not be in compliance with the standard. So I would suggest to whatever the design you're doing. Suppose you're going to make sure that you're going to put a cable tray and you're going to route it in this specific route. You're going to take that cable details. It is better to put it in the design stage, and also you fix a margin like 10 percentage. It is going to increase, and you put that 10 percentage in the whatever design, whatever calculation you're going to do. You do that, but in site conditions, you make sure it is coming to that, or if it is going to reduce or increase, you again update to it and you check whether it is again safe or not. You have to do that again.
Nandu, we are on time. We are now 1.5 hours. It's almost coming to 1.5 hours. Wonderful session. I'm sure this software is going to make every electrical designer very convenient. I'm sure there'll be a lot of demand for your software that you're demonstrated here. And we will come back, maybe have a series 2 on this later, maybe next year,
Sir,
2026.
only one point, sir. Before that, there is one final question from UB Tech about
Mhm.
is there any thumb rule that aluminum cables below 25 amps should not be considered in design instead of copper cables? This is a requirement from, for that alone, I'll give a comment that this is a requirement from NBC. So there is no specific reason. The only reason why the committee has decided to put any specific answer is that people are not derating the aluminum cables when you are putting instead of copper. So if you're going to put aluminum instead of copper, if you derate it properly, it's not a problem. But since generally in India we are not derating at all, they are going to put some one size higher aluminum cable. They are going to put that as some small calculation. That is the only reason why they are saying you should not use it. So that is the only reason. There is no other reasons for it. Yes, we can probably, yes,
Uh,
sir. Over to you.
Wonderful. The next webinar, mistakes. What is that we have? Yeah, mistakes in termination and cable entry cost lives. Very interesting topic by Krish Theobald, who is another young trainer. So next Saturday we'll see you all again for the same time. And wonderful to have you, Nandu, and a lot of appreciation for your talent and the presentation that you have made that you can see in your chat box. I would request everyone to join NFE. Please visit our website www.nfees.org. Become a member, interact with Nandu and many other engineers. If you look at our WhatsApp, we have different groups. If you want technical questions, you can always raise the technical questions. It's a wonderful platform for all the electrical engineer and safety professional. Please do join. And thank you all once again. I look forward for your participation in upcoming webinars. Have a wonderful weekend. Stay safe. Thank you. Bye-bye.